Now it really so happens is that here I did not really vary the number of hidden layer neurons. Those were fixed, and that's another architectural parameter. It can be said that keep a arbitrarily large number of neurons. So I don't know the number of neurons, and it's a parameter already over here that is fixed. So you can say that keep a very large number of neurons. So these are very large number of neurons. And if these neurons are useless, so all these weights which are incoming to these neurons, so for all these, C will become 0. And for all these, C will become 0. Genetic algorithm can do that. But then if I take arbitrarily large number of neurons, my genotype length is arbitrarily large, and we know it's a curse of dimensionality. So optimizing a very large individual is going to be a painstaking effort. It's curse of dimensionality, so I cannot have arbitrarily large number of neurons. And therefore now what I would like to do probably is to modify this such that I can have a variable number of neurons as well. And not only can I have a variable number of neurons, as well I can do an evolution such that the evolution decides the additional parameter, which is the number of neurons without the genomics length being arbitrarily large. So this time what I do is I again take a neural network and I try to encode it up. So let's take a phenotype and a genotype. So let's start off with a phenotype. So input, hidden output, and some connections around this thing over here. The other is not present. Now, instead of modeling in every weight, this time what I'll do is I'll try to model every neuron. So let us try to model this neuron. And a neural network is nothing but a collection of neurons. So I'll do the encoding for one neuron and I'll embed all the neurons, hidden layer neurons, and then I'll see what happens. So let's only model this neuron. So this neuron is given by input, output. And the weights that it has is whether it's present or not, W2 whether it's present or not, and W3 whether it's present or not. So that's one neuron. So this one is this neuron over here, and the neural network is nothing but a collection of these neurons. So let me model this neuron and then let me have multiple neurons. So as of now, this is of course the phenotype. This is one neuron shown explicitly, but this entire is a phenotype. So let's model one neuron. So that's W1C1, W2C2, and W3C3. And similarly, let's model the other neuron. So this is for neuron 1. And so on. So I say variable number of neurons. So if there are I inputs and O outputs, the size of this neuron is all the weights from, I think I forgot the bias. I forgot the bias, of course. So W0, C0. Let's just add it on 1. So I plus 1 connections from input to hidden layer, where 1 is for the bias. O outputs. So that's a plus O. And these are the number of weights value and equal number of connection value. So this is the size of this neuron, the same as the size of this neurons. So for K neurons, the genetic individual size is this is for one neuron. And this is for K neurons. Okay, so the problem is this K is variable. So my population is now of a variable size. Every neural network will have a different number of neurons, and for the first time we'll be seeing neural network which have different size, or we'll be seeing individuals which are of a variable length. So my population pool will look something like this. First individual with smaller number of neurons, second individuals with too many neurons, the third with a moderate number of neurons, the fourth with a very small number of neurons, the fifth again with too many neurons, or my individual size is variable. If I take any one of these individuals, let's start applying genetic algorithm. The first thing that I do is, of course, the genotype to phenotype. So I'll take the same individual over here, and let's say that it had 3 neurons. So this was the encoding for neuron 1, this was the encoding for neuron 2, and this was the encoding for neuron 3. So I load my favorite machine learning library, make these 3 neurons that's a bias. So I'll copy the weights and whether the connections is present or not for this neuron. I'll copy the weights and whether connection is present or not for this neuron. I'll copy the weights and whether the connection is present or not for this neuron. And then, of course, I'll make this neural network and I'll do exactly the same thing as before. So fitness function evaluation is not a problem. I can do a fitness function evaluation. The variable size of the population is not a problem. For here, they would have been, instead of 3 neurons, they would have been 7 neurons. For this one, they would have been just 2 neurons. For this one, just 1 neuron maybe, but I can still do it. I can still use my favorite neural network library in order to find out what the phenotypic is. So that's a genotype, and I converted it into a phenotype. And therefore I can get the loss function. So obviously my loss function will be pretty much similar now. So if this is theta I, the loss function or the fitness value of theta I will be the MSE, training data, the ANN, plus the regularization in terms of the number of connections, plus the weight values, two looked at previously, absolute value, plus the number of neurons. So number of neurons are proportional to the size. So I try to minimize the loss function, I try to get lesser number of connections, I try to get lesser weight values, and I also try to get in smaller total number of neurons. So I try to reduce the number of neurons, which are now variable. Now let's see whether there will be a problem or not. Let me see whether there will be a problem or not, because it's the first time we're looking at neural networks which are of different size. So fitness evaluation, if there wasn't a problem, we've already done that. Deciding the rank from fitness value doesn't matter. Scaling, n+1 minus rank, normalized, it's okay. Selection, I can do that. Then comes major two operators, crossover and mutation. So let's look at the two operators. So first let's look at crossover. Now so far what we were doing was first parent, second parent, and then we said that child 1 is equal to a random number times parent 1 plus 1 minus the same random number times parent 2, and child 2 is equal to random number times parent 2 plus 1 minus same random number times parent 1. So where R was uniform between 0 and 1. Now I cannot do that because the sizes are unequal. So now the sizes are unequal, so I cannot apply that. And because I cannot do that, so I will have to do something about it probably. The sizes are unequal. I cannot just apply a crossover like this. So my individual representation is a number of neurons, and every neuron is a collection of weights and biases. So let's put it like this way. So this is my parent 1 and this is my parent 2, where parent 1 eventually has a neuron 1, a neuron 2, a neuron 3, and a neuron 4. And parent 2 potentially has just a neuron 1, a neuron 2, and a neuron, let's say just a neuron 1 and a neuron 2. So now, how do you do the crossover? You can use any technique in order to do that. Like one thing which I could say is there are 4 neurons in the first, there are 2 neurons in the second. So let's create 2 children with average number of neurons. If there's or even odd, then you can add it to any one. So 3 neurons for child 1 and 3 neurons for child 2. Let's say just the average. You can use any technique. And let's give codes to the neurons. So this is A, B, C, D, and this is 1, 2. So first I apply a scattered crossover. So with some probability, A goes here, 1 goes here, and with some probability, these two invert. So till I can apply scattered crossover, there is no problem. Now, how many spaces do I have? 2. How many neurons are there? 2. So just distribute them randomly. Let's say C goes here and D goes here. So that's your child 1 and child 2. If you want, then the size of the neuron is equal, and if you want, you can do a scattered crossover here. The size of this neuron is the same as the size of this neuron. If you want, you can additionally do a scattered crossover there or an arithmetic crossover there. So that's how I can handle in the crossover. So not a problem. The neurons are of unequal sizes. So till the size is equal, you do a normal crossover, and for the rest, just divide them randomly. So I could also till here I do a normal crossover, and C and D, I just decide randomly which goes to first, whether it goes to first, whether it goes to second for both of them. So maybe both go to first or both go to second, not a problem. So crossover can be handled in case of a variable size of the neural network architecture. Now let's talk about the mutation. Now, normally it will appear that I again have the same thing. A neuron 1, a neuron 2, a neuron 3, and a neuron 4. And let me just make it around over here, and some weights around over here. So this is the genotype, this is the phenotype. So one thing that can happen is that, let's say this weight was plus 0.9. I can apply a Gaussian mutation to it, and so this was the weight in neuron 2. So somewhere here was plus 0.9, and I reduce and add a Gaussian noise, so it becomes 0.85, or it becomes 0.85. This kind of mutation is called as parametric mutation, which changes the values of weights, and it means the weights and biases. Sometimes this weight wouldn't have been there, so the C was 0, I can make at C as 1. That's another mutation which is possible. Now, for the first time, the genetic algorithm is actually modifying the architecture. For the first time, the neural network, for the first time, the genetic algorithm is doing something more than what you would expect. For the first time, the genetic algorithm is also modifying the architecture, and therefore, along with parametric mutation, I will also have structural mutation. So let's apply it over here. So the first structural mutation that can happen is I need to change the structure. So I add a neuron. So I just add a new neuron. So the same things which don't change, except for that I added a neuron. So this neuron got added. And in terms of what it will look in the phenotype, in the genotype is, so I already had a neuron 1, a neuron 2, a neuron 3, a neuron 4. I also have a new neuron 5. So this is produced for mutation. So this new neuron is the one that's produced from mutation, and this is produced from mutation. And this is called as the add neuron structural mutation. There's another structural mutation, of course, and that's exactly the opposite. So this time what I can do is I can delete a neuron. So I take the same neural network. So I take this one, I take this one, and I take this one, and I delete this one. And the weights and the connections become exactly the same. So this one is delete neuron. Structural mutation. And if you want to have a look at what is it in the genotype, then of course it is, I had a Neuron 1, it remained as it is. Neuron 2 got deleted, so there's just a neuron 3 and a neuron 4. Okay, so that's what is the mutation operator. So summarizing, so earlier mutation was just adding a Gaussian noise. Now mutation is of two types. The first one, which is called as parametric mutation, and the other one is called as the structural mutation. So for every individual, I make a random selection, whether I have to apply structural or I have to apply a parametric, I make a random selection. So the structural mutation was interesting. It changed the structure, so it either added a neuron or it deleted a neuron. The parametric was, of course, just to change the weights, which by default mean the biases as well. I'm not differentiating between the two. And of course, it could change the C value, so change the presence of connection. It can be said that it's actually changing the architecture, but when the architecture is just a parameter, so changing that parameter changes the architecture, we just would call it as something which is parametric. It may appear as something weird that what's a structural mutation? And the answer is it's actually pretty much de facto. Most of the problems that we deal with in genetic algorithms are just parametric, but sometimes you deal with problems which have a structural element to them, and whenever they have a structural element to them, then you know, and by default there are always two types of mutation, the one that changes the parameter and the one that changes the structure. If you don't have any mutation that changes the structure, the neural network is not something which will fancy around and try to explore a newer architecture, and it'll be left with whatever architecture is there by default, which is initially. Now, creation of a new population pool after crossover mutation, it only depends upon the fitness function value. The top K survive, so the top N survive, the top N individual from parent and children survive. Sometimes the children become the new population pool. In both cases, it's easy to do, so there's absolutely nothing to be mentioned about it. So this one is a good example wherein we use a genetic algorithm of variable sizes, and the genetic algorithm had a variable size because every neural network had a different size of the neural network. But we adapted the operators, and by adapting the operators, I still could get in exactly what I wanted. I could still get in my evolution done, and because I could get evolution done still, I could use the genetic algorithm to evolve also the architecture of a neural network